is September 30th. So you could write this September 30th right on your page. Make sure you flip it so that you're looking at the same side as I am. This is a new unit, but it looks at a lot of the same stuff we did in our previous unit. So our next unit is called Irrational Numbers, and we're going to look at these number families and how numbers are placed into a specific family. The first family group is called natural numbers. And I think you have a space. You have to write this in yourself. So some of your notes are written for you, and some of it there's space for you to write. Yes? Pen or pencil? Sorry? So the first number family is called the natural numbers. And they decided on this name because these were the numbers that first appeared naturally. People started counting things, and those were the first numbers that people ran into. They were like, ooh, I've got 10 fingers. So they counted to 10. Those natural numbers went 1, 2, 3, 4, and they keep on going. Now, for each of these families, mathematicians have also come up with a special symbol to represent them. For natural numbers, it's a capital N with 2 lines on one side like that. So mathematicians are a little bit lazy, and they don't like English. Like, they didn't like reading books or writing essays. So even sometimes with words, they're like, I'm too lazy to write out naturals. I'm going to create a symbol, so I just have to write one thing so it's quicker. Just drew 2 lines on the one side. And then the next key number to get sort of invented in the history of math was 0. Right? People had counting numbers, right? Here's a guy, he goes into battle, he has 3 fingers. Okay? He ends his battle and 3 of his fingers got cut off. And now he has trouble counting. Okay? But he didn't have a number. Someone said, how many fingers do you have? And he was like, Right? And so they introduced, not because of battles and losing fingers, but it became important to have a 0. To say, they're all gone. There's none left. So 0 got added, and these are our whole numbers. Look at that. Eventually, though, just having 0 wasn't enough as well. Because like, if you moved to Canada, right now you woke up and it was how warm out? Like 3 degrees plus 1, it was cold. And pretty soon, the temperature's going to go down, and it's going to get to 0, and things are going to freeze. And then it's going to go right down to -20 the next day. Exactly. And so negative numbers needed to be added in. And when we add all the negative numbers, all the natural numbers, and 0 together, we get the integers. Now, for the symbol for integers, you have choice. Usually in grade 9, people like to use the I because integer starts with I. But internationally, it's more common to see integers with a Z. And that's because, well, it comes from the German word for numbers, which is Zahlen, which starts with Z. And so internationally, integers are seen as Z. But you can choose either of those symbols when you're writing yours. Next up, another guy went into battle. He started with 4 fingers. After the battle, he lost 2 fingers, and another one was just clipped off halfway. So now they say, well, how many fingers do you have? He couldn't really say he had 2 fingers because one was missing part of it. Couldn't really say he had 1 finger because he still had some of the other one. So we have a necessity for fractions. And any number that can be written as a fraction is considered a rational number. And we use a big Q for rational number because if you write it as a fraction, fraction is another way of showing dividing, right? 1/2 is 1 divided by 2. And so any number that you can write as a fraction is considered a rational number. We also know that every decimal that ends, so every decimal that terminates, remember we practiced 0.12, that ended in the thousandths, and we practiced that you could write that as a fraction over 1,000. Oh, and any decimal that repeats, 0.2 repeated is 2/9. Give me a double 2 numbers. 0.15 repeated is 15/99. 3 numbers. Any guesses? 1. Oh, that's not a 1, that's a 2. 271 repeated would be any guesses what that would be as a fraction? If 2 repeated is 2/9, 0.15, thank you. Yes, 271/999. So any decimal that repeats itself or any decimal that terminates can be written as a fraction, and any number that can be written as a fraction is considered a rational number. Could you write the number 5, which is a whole number? It's a natural number. It's an integer. Could you write it as a fraction? 5 is equal to 5/1. 5 divided by 1 is still 5. So we consider 5 a rational number as well. So the interesting thing about mathematicians, different than your grouping, right? You were, and I kind of forced you to try to say, is it going to be in this one or this one? But some of those numbers you felt like, oh, it could be in both. For mathematicians, numbers can be in more than one. And finally, our last 2 groupings, irrationals and then reals. Irrational numbers are numbers that don't repeat and never end. So on the numbers that I gave you, we had some that were ... that kept on going. Those would become or be called irrational numbers. The symbol for irrational numbers is the same symbol as rational numbers with a bar over top. And that bar over top in math says not rational numbers. You'll see in some textbooks, they'll put a squiggle in front of the rational numbers. The squiggle in front means not. See, again, mathematicians are like, I don't want to write the word not because it's 3 letters and it would take me all of a half a second. So I'll make a line instead. So decimals that don't terminate or repeat, a lot of square roots fit into irrational numbers. Not all square roots, because the square root of 9, that's just 3. It's a whole number. But the square root of 2, type that in your calculator and you look at it, and I'll just show you if my calculator opens up. It's not happy today. Okay, never mind. Square root of 2, if you type it in your calculator, goes 1.141 and keeps on going. And if you looked at it, you'd see no pattern. So then you'd have to say, it looks like it doesn't repeat. It looks like it doesn't have a pattern. So then it is an irrational number. And finally, considering all the numbers together, these are our real numbers. Don't move yet, okay. Good? So now on the next page, I'd like you to put a box around the diagram that's there. And we categorize the numbers this way, because our natural numbers are inside of our whole numbers, because whole numbers are 0, 1, 2, 3, 4, 5. Natural numbers are 1, 2, 3, 4, 5. The only thing different between natural numbers and whole numbers is you add 0. And then integers include the whole numbers, which is 0, and the natural numbers, which is 1, 2, 3, 4, 5. And in the integers, the next biggest circle, you add your negative whole numbers. Then after integers, the next circle is Q. You add all the fractions that weren't whole numbers, positive or negative. Those are your rational numbers. So you have one circle that's separated into 4 different things, and then irrational numbers are their own separate circle. So decimals that go on forever, that don't repeat, numbers like pi or square roots, those are irrational numbers. Rational numbers you can write as a fraction. Irrational numbers you can't. So, turn your page over. Your first example. You're going to decide just whether you have irrational numbers or rational numbers. Okay, we'll do a check. How did you do? Is the first one, 3/4, a rational or irrational number? Rational. So you can just put the symbol underneath, or if you wanted to write out the word, you could. What about the square root of 2? Irrational. Put that symbol underneath that one. 5.456. It is rational, because it's a decimal that stops. It's going to be a rational number. Pi. Irrational. If you type pi into your calculator and push enter, you get 3.1415965 and so on. But it seems like a bunch of random numbers. What about 4/9? Can that be written as a fraction? It is a fraction. 4/9 is a fraction already. And now we have another square root. But the square root of 4 is equal to 2. And 2 can be written as a fraction, 2 divided by 1. This one was a tough one. It's a square root, but it's still a rational number. So we see the importance of, in math, we have to simplify things. And if we have things simplified, then we can easily tell which family it belongs to. Right now, we're just looking at 2 bigger groups, irrational and rational. 3.59293135. Is that one repeating? Or does those just look like a bunch of random numbers? Just looks like a bunch of random numbers, so we would put that one as irrational. And the dot, dot, dot at the end means that it keeps going. Can you see the next one looks like it's repeating? 1, 3, 1, 3, 1, 3, 1, 3. That one would be rational. For the next one, write out all the families it belongs to. Naturals, wholes, integers, rationals, irrationals, and real numbers. And just for fun, remember we had that square root of negative 9. Add that one in, that's one that we saw that doesn't belong to any family because it's not a real number. And there's no extra handouts today, so you should be good. We're just going to finish this. So for example, I'll do the first one with you. 44 is a natural number. It's also a whole number. It's also an integer. It's also a fraction. And it's also a real number. It's all 5 of those. So for each of these, we're trying to do all of them. So one of the things, and one of the reasons this diagram is really helpful, like once you found out that 44 is a natural number, it's going to go into all of these categories. So one of the things you'll do, if you find something is a rational number in one of those 4, it might be in more than one. Well, as we saw with 44, if we go forward to the next one, negative 3, well, negative 3 is not a natural number. It's not a whole number, but the first one it is an integer. And because integers in the rational, you'd also include rational, and you'd also include real. So one of the things that I find helpful is sort of, right, thinking of, I'm going to do purple here, right? I think of these the one circle, the bigger circle with the 4, those are your rational numbers, and your irrational numbers. Those are 2 separations. And then inside your rational numbers, there's 4 groups. So as soon as I figure out what the smallest group something is in, 0, it's a rational number. Which is the smallest group? It's not a natural number, but whole numbers include 0. So once I've got whole, then I also have integer and also have rational numbers. And then always, real numbers are all numbers. So I start 5 ninths. Is it rational or irrational? It's rational. It's one of these 4. It's not a natural number, not a whole number, not an integer. First one is just rational number. And then add real number as well. The next one doesn't have a pattern, and it has a dot, dot, dot at the end to say that it keeps going. So now you're in irrational numbers, and still would be a real number. Negative 2.3. It's a decimal that terminates. So it's going to be in your rational numbers. It's not a natural number. It's not a whole number. It's not an integer. Integers are positive and negative whole number. The first one it can be rational number and real number. So we're going to look a little bit at the next section of notes. I'm not sure if we'll finish it because there's only a couple minutes left. But in the next section we have some other interesting families. These are just groupings that describe something, but they're not an actual number family in order to organize numbers. In order to organize numbers, we split them into rational and irrational, but we have some other special numbers that are worth talking about. First one is prime numbers. Have you heard of prime numbers before? Okay, prime numbers are a number that's only divisible by itself. Okay? The interesting thing about prime numbers, you inadvertently use prime numbers all the time. Security on your cell phone requires large prime numbers. You don't want someone else to get your phone and be able to break into it and then take all your money from your bank account, $8.03, and steal it. That would be bad. Right? So we need to have passwords to protect us, and those passwords are based on prime numbers. Some of the first prime numbers are easy to figure out, but finding bigger prime numbers actually takes a lot of thinking, a lot of math. You have to know your times table, but then if I say something like, is 99 a prime number? Or is there something that times by itself to get 99? 99 isn't, because it's also 9 times 11. But not so easy if I would say 97. Is 97 something times something? Or is it just 1 times 97? If it's just 1 times 97, then it's a prime number. Notice that 1 is not considered a prime number. Perfect numbers. This is just interesting. But in math, we call something a perfect number if we look at all the numbers that you could get to multiply 6, but not including 6. Would you agree that 6 is equal to 1 times 6, and 6 is also equal to 2 times 3? Those are the only ways you can get 6 with whole numbers. If you add up all the ones except for the one that it is, except for 6, 1 plus 2 plus 3 is equal to 6. It's just a weird coincidence. For 28, 28 is 1 times 28, 2 times 14, and 4 times 7. And if you add 1 plus 2 plus 4 plus 7 plus 14, you get 28. It's the second perfect number. And after those first two, it's pretty hard to find other perfect numbers. There's only 4 of them if you go up to 10,000. And trying to find the next one would be really, really hard. Palindrome numbers, this really is just, these are hardly ever used. It's just if you can write the numbers same way forward and backwards, it is a palindrome number. Right? They also use palindromes in English. Race car. Read it backwards. Race car. Isn't that cool? Some people's names are palindromes. Anna.